Okay, let's do a little bit of practice with this stuff. All right. So we know this equation is basically how much heat over time is going to be equal to constant times the area of a surface times the change of temperature between the two temperatures divided by the thickness of that material, right? So A and D are related to the same material. And this is all related to the exact same diagram or series of information that we used in the last example. I'm going to make a picture and send it to you anyway. So we're talking about something like this, guys. We're talking about something like this, right? So if you've got a material that is here in this area of thickness D, so some space between these two temperatures, right? So maybe this is a duct between two rooms or whatever, right? Or it's you know what, let's just call it a solid. It's some solid between these two temperatures. Then heat is going to transfer from T2 to T1 if T2 is greater, right? Moving through this area of area A. So we find the cross sectional area. So it's like we make one slice out of it. So that's what cross sectional area is, like taking a slice. If we take one slice out of this object, it's going to have area A. It's going to have thickness D. So that's all going to kind of work in this equation, right? So let's find an example that we can kind of do to figure out something, right? So let's say we want to know K, right? So let's say we don't know K. Okay. Wow. Is it okay if we don't know K? We're going to solve for K. All right. So we don't know what K is, but maybe we know that, we have 80 joules per second on the left side equals Q over T, right? Of energy, right? Maybe we also know that the area is the cross sectional area. That's going to be in square meters. No, it's in regular meters. Yeah, it's in square meters. I literally made this. I made this wrong. There we go. Fix that. Put a little squared there. We'll just leave that. There we go. Sometimes we make mistakes, guys. There you go, meter squared. Okay. So the area, I don't know, let's call it 25 meters squared. Maybe it's a square that's 5 by 5, right? So maybe we've got ourselves, let's make a little cross section here. We've got a little cross section like this. And our little cross section is, 5 meters by 5, excuse me, by 5 meters, right? So it's 5 by 5. So that gives us a cross sectional area of 25 meters per second, or sorry, meters squared. What is wrong with me? And then let's say that the thickness here is 2 meters, right? So we'll say that D is then 2 meters. Okay. So we're using a pretty thin material. So maybe we just have like a sheet of something. Okay. It's actually pretty thick. 2 meters is quite thick. That's like a human height. That's like 6 feet tall. Right. So we've got Q over T. So we've got this. We've got D. We've got A. Now, what if I told you that on, we'll call it T2, the left side, our material is at a temperature of, I don't know, let's call it 100 degrees Celsius. And let's just keep this simple, right? On the right side, our material is 50 degrees Celsius. Okay. So what we need to do is figure out what is the thermal conductivity constant of this material. And we can ask ourselves even another question. Is this material a conductor or an insulator? If it's a good conductor, it'll have a pretty high K value. If it's a bad conductor, aka an insulator, it might have a low K value. So let's plug in and find out, shall we? All right, time to do some math. Here we go. Let's plug in all of our stuff. So we know right now that we've got, what color are we right now? Let's change colors. We've got 80 joule seconds worth of energy, 80 watts worth of thermal energy, and it's equal to K, which is what we're solving for, right? So we'll circle that for now, times A, which we know is 25 meters squared, times the change in T. What's 100 minus 50? It's 50 degrees. So times 50 degrees Celsius. Cool. All divided by D, which in this case is our thickness of 2 meters. Okay, so let's see if we can't figure out how to get K on its own. But first, let's do some simplification. So we're going to leave the 80 joule seconds, aka watts. Again, I'm going to make this simple so that you're just plugging stuff in, right? And then rearranging an equation. Equals K, we can pull that out, times 25 times 50 divided by 2. 50 divided by 2, because we can use order of operations here, right? So, but it doesn't really matter what we do because all of these things are equivalent. So 50 divided by 2 is 25. So we've got 25 times 25, right? Which is what? I'm giving you a second to do it on your calculator because I forget the actual number. 625. There we go. Okay. So we end up with 625. And what did we do when we had this going on here? We were taking meters divided by meters. So we have meters times degrees Celsius. Again, the units aren't really going to matter, you guys. I'm not going to care a lot about units on this one. I just want you to try and get the right math, okay? So we can come up with the right values. Okay, so what we know right now is that 625 meter degrees Celsius times K equals 80 watts, 80 joules per second, right? So sweet, let's solve for K. How do we do that? We need to solve for K, right? In order to solve for K, we are going to need to divide by 625 meter degrees Celsiuses on both sides. I wrote 620 m, 625 meter degrees Celsiuses, right? So 80 divided by 625 is going to be equal to K. So you can already see that our number is going to be exceptionally small, right? Okay. I just did the math backwards. 80 divided by 625. There we go. Okay. So we're going to end up with 80 divided by 625 is 0.128. Okay. And that's going to be equal to K. Now, remember, we canceled these units out when we were using this the last time. So we've got joules per second. So divided by meters times Celsius. So what we end up with is joules per meter second degree Celsius. And that's our unit for K. Pretty weird, right? That is our unit for K. It works out. It's the only way for the math to make sense, right? So that's the unit you'd get for K. So anytime you see K values, they should be in joules per meter degree, which actually can be rewritten, right? Because remember, joules per second is the same as watts. So you could say watts per meter degree Celsius would be the acceptable unit for K. So we're just going to roll with that for now. I understand that that's probably very confusing to you, but I wanted you to see kind of how this formula is manipulated, right? So what we ended up finding was a very low value of K, right? So if we're asking ourselves, is this material a conductor? Sorry, everything is a conductor. It's whether it's a good conductor. A good conductor. We're going to say very easily, no. In fact, this material is actually a pretty good insulator, which means that it does not conduct energy very well. It's not allowing thermal energy to move very easily through the system. So we might say, hey, this is a good material to use, for packaging your hot beverages or making your coolers out of or whatever. Now, I don't know what this material is. We just made it up. It's mystery material, right? But we can roll with that. Okay. So there's one example. Okay, so here's another example of a problem, right? So what if I told you that we have a doorway or a window? Let's do a window. Can we do a window? Let's do a window. It's easier to draw. So we've got ourselves a window. Okay, a window to the outside, right? So there's our window. And it's warmer in your house than it is outside your house, right? So energy, I should draw this a different way. So energy is going to be leaving your house, basically. Thermal energy is leaving your house. This is like an actual problem that you could relate to. So maybe we have, let's draw your window like this. Try really hard to make the thickness actually make sense. That would be the side of the window. You don't normally see that. Okay, cool. Great, 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 great. Cool. Good, 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 good. Okay, cool. So there's our window, right? And this is inside your house. And over here is outside your house. And let's make it the winter. So we'll put some snow on the ground or whatever, right? We can put like a tree over there, something, so that it kind of looks normal. Why isn't there a brown color? There isn't a brown color. So we'll do it. It'll be a gray tree. Whoops. Gray tree. And look, it's got a branch and everything. Look at that. Look at this right here. Look at this. It's the winter time, right? So let's just say it's a pine tree. Okay. It's a pine tree. And, like comes to a point and then like, like this, like that. Yeah, great. It's really awesome. It's very, very well done. Great job. As you can tell, I actually used to be a graphic artist and now I'm a science teacher. Lol. Okay. There we go. Look at that. He's covered in snow and everything. Yeah, it's beautiful. Wonderful. Everybody understands. Okay, cool. So heat is going to move this way, right? That's going to be the direction of your Q movement in this case. Let's just put a Q on there. There we go, right? So T1 is in here. And let's say that inside your house, it's, I don't know, 75 degrees Celsius or Fahrenheit, rather. So what is that in Celsius? That's like 24 degrees. So let's say it's 24 degrees Celsius. Okay. Normally I wouldn't really care about temperature, but in this case, the equations don't really work if we use Fahrenheit. So we're just going to use Celsius. Okay. And then outside it's colder. So let's say since it's snow on the ground, obviously it has to be at least 0 degrees Celsius. So let's say that it's, I don't know, -4 degrees Celsius, and that's your T2. Cool. All right, nice. Okay, so what we want to figure out is, okay, first of all, what's our window made out of? Our window's made out of glass, right? So we're going to be saying, all right, through this window, heat is moving, but how much heat is moving, right? So if I tell you the area of your window, area of your window is probably going to be something like, if it's a regular old window, the cross sectional area, which would be like one slice of it. So your glass, that's how much glass is exposed to heat. Let's say that your window is something like 2 meters wide and 4 meters tall. So your area of your window is going to be 8 meters squared. And let's say the thickness of your window, I don't know, it's going to be in centimeters. So it's probably only going to be, let's say it's like 30 centimeters, right? So that's 0.03 meters. There we go. I have to erase this because I'm using 0.03 meters. There we go. 30 centimeters, 0.03 meters. Sorry, I literally paused just to look that up because sometimes even I forget unit conversion, right? So your D is 0.03. So D is 0.03. All right. We can then say, okay, we know what K is, right? So these are our K values. So that we can say, okay, we know that K for glass. So we can write K glass like that is equal to 0.84, and it's in watt per meter degree Celsius, which is joules per second per meter degree Celsius. Doesn't really matter. Okay. So we'll just call it that. All right. So we've got our A. We've got our D. We can find delta T. We know what K is. Perfect. So now we're going to find out what is QT, right? So how much heat is going to escape per second, right? So this might be saying like, okay, how much heat is escaping per second? So how much heat escapes per second? There we go. So we're actually going to try and calculate the efficiency, the energy efficiency of our windows, basically, right? So we're looking for the QT value. We're trying to solve for QT. So all we have to do is plug everything in. So let's make the pen width a little smaller. And let's get to plug-in, shall we? So let's use this weird color here. So we know that QT is what we're solving for. QT equals to what? Well, K, which we know is 0.84. Okay. I'm going to include units because I can't not do it. It's just a thing. I don't know. Sorry. Times A, which is 8 meters squared, times change in T. In this case, your change in T is actually 24 minus -4, which is 28. Right? 28 degrees Celsius, like that. And then we're going to divide by what? D, which is 0.03, 0.03 meters. There we go. So actually, all we have to do is plug it in, and we've got our answer, right? It's going to come out exactly as we want it to. So I'm going to actually multiply the whole top and then show you what that looks like. So 0.84 times 8 times 28. Okay, so we've got 188. Wow, sorry. Got a little freeze there. 188 and 4/25ths. I need to use my math. And 0.16 divided by 0.03 meters is going to be equal to Q over T, which is, again, this is the how much heat per second, right? What are the units on this? Oh, we have 188.16 divided by 0.03 meters, right? So what we need to do is take a look at what we've got up here on the top. So what we've got up here on the top is watt meters squared degrees Celsius per meters degrees Celsius. So based on what we've just done on the top, we are going to get rid of 1 meter, right? So we've got a meter in the denominator. So we cancel that out, get rid of the squared, right? So that leaves us with watt meters, degrees Celsius. But then we've got degrees Celsius on both. So we've got watt meters on top divided by meters. So what's going to end up happening is we're going to end up with meters divided by meters here, and we're going to end up with just watts, right? Which makes a ton of sense because on this side, Q over T is literally in watts. So 188.16 divided by 0.03 is actually a huge number. So let's take the answer over here. We're going to end up with 6,272 watts, right? So that's how many, which would be 6,272 joules per second of heat loss. So what I'm telling you here is that you're losing a whole bunch of energy out of your glass window in this particular case. So we should probably try and figure out something else that we should do. Okay, so maybe you need to put something over your windows or get thermal curtains or replace your windows or something because, or use a thicker glass because obviously our window is allowing a lot of energy to transfer through it per second. Now, is this like it would be in real life? Probably not. I actually don't know how efficient or inefficient your glass windows would be, but most people use double pane glass or triple pane glass, and a lot of times they put air, they trap air like in a vacuum between the glass because that is going to be a really, really, really good insulator, right? So air has much lower thermal conductivity. So putting that in there would actually mean that you're not going to lose very much energy if you put that air in there. It's going to make for a very small equation, right? We also, you might notice, the biggest factor affecting this is that we're dividing a big number by an even smaller number, which is basically like multiplying. So you'd probably want to use a lot thicker glass um, to make this make some sense, right? So if you the thicker the glass you use here is going to give you a more efficient window, which you could probably figure it out. So anyway, this allows us to then kind of analyze situations and figure out like, okay, like what's a good conductor, what's a good insulator, how do we use them, right? You don't want to make silver windows, do you? Because those would just allow energy to fly out, right? And if you make all styrofoam windows or all air windows, that'd be great. But the problem is, if you make air windows, you've basically just got a hole in your house, don't you? So you'd have to actually trap the air and make it not moving, right? And styrofoam windows have other issues, like you could punch through them and stuff. So anyway, this has been a quick walkthrough of how to do some math problems, and hopefully this helps you. We're literally just doing plugging and chugging. So, right, that's what I'm going to be having you do is just a couple practice plug and chug type of problems. Okay, good luck with that.